Still, the relief masked a profound question. If C is baked into the meter, what's left that we truly measure that ties together electromagnetism, quantum mechanics, and relativity? Enter a dimensionless constant, one that can't be redefined away by changing units. The fine structure constant, alpha, 1137 and change, sets the scale of atomic structure. It lives in the spacing of spectral lines and the strength of electromagnetic interactions. You can't hide it in a definition, because it's a pure ratio. Here S where the stakes rise again. If alpha drifts, chemistry retunes. Electrons nestle closer or farther from nuclei. Spectral fingerprints shift. Stars fuse differently. A minuscule change over billions of years would leave quiet graffiti in the sky and in the rocks. And unlike C, alpha can be hunted in many places. In astrophysical spectra, in the ruins of a 2-billion-year-old natural nuclear reactor, and in the beat notes between today's best clocks. But let's not jump too fast. There's one more twist in the meter-lied story that teaches caution. After 1983, when someone reported a variation in C, critics could rightly answer, "You're reporting how your apparatus measures length and time within the new definitions. Any drift lives in your materials, your lasers, your electronics, or in nature's constants that those devices depend on." That's the subtle pivot. We stopped asking, "Is C changing?" and started asking, "Are the deeper, dimensionless couplings changing?" Meanwhile, something else was happening in the background. As lasers stabilized and frequency standards improved, labs discovered that every component had a personality. A fiber's refractive index twitched with strain. Coatings on mirrors aged under light. Vacuum chambers that seemed quiet had outgassing rhythms. Metrologists became part physicist, part therapist, coaxing instruments into silence long enough to hear the universe. And in those silences, they heard nothing obvious. But nothing isn't the end of the story. Nothing sets the limits that define the hunt. Okay, stakes, action, and the impact of a definition. The day the meter lied wasn't a scandal, it was a turning point. We fixed a number to anchor measurement. We lost a direct test. Therefore, we needed a new witness that nature couldn't duck with a unit change. Alpha raised its hand. In the next act, that whispering constant steps into the light and distant quasars, light that left when the universe was young, become our cross-examination. The fine structure whispers, alpha's uneasy consistency. Alpha isn't a speed or a mass. It's a ratio that tells electrons how tightly to hug a nucleus and how photons talk to charges. Change alpha a hair and hydrogen's spectral lines scoot. Change it more and stars rehearse a different script. That's why this constant is the witness we needed. You can't redefine a pure number away. If it moves, the universe leaves receipts. And here's the thing, you'd see it everywhere at once. In quasar barcodes, in a 2-billion-year-old reactor's ash, and in the way today's best clocks quietly disagree. So where do you look? First, the sky. Distant quasars light up clouds of gas between us and them, carving barcode patterns of absorption lines. Those lines aren't just pretty, they're rulers etched into the past. In the late 1990s and early 2000s, a group started stacking those rulers using the many-multiplet method. Instead of relying on a single doublet from, say, magnesium, they mixed transitions from different ions. Iron, chromium, nickel, each with a different sensitivity to alpha. If alpha changed, the spacing between these lines would shift in a telltale way, across species, not just within one. The initial hint was strange. Keck Observatory's spectra suggested alpha might have been smaller when the universe was younger. Then new data from the Very Large Telescope, looking in a different part of the sky, nudged the other way, alpha slightly larger. Put together, the anomaly didn't average to zero. It arranged itself like a dipole. One half of the sky preferred a nudge up, the other a nudge down, at roughly parts per million. Not a loud shout, but a whisper with direction, consistent with the Webb-Murphy analyses that sparked 2 decades of follow-up. Here S where the human part kicks in. In one office, a postdoc scratches out sensitivity coefficients and says, "That pattern is hard to fake." In another, a spectroscopist groans, "It's the wavelength calibration." Old-school lamps that mark the pixel-to-angstrom mapping can have tiny distortions across orders, slit illumination shifts, temperature gradients inside the spectrograph bend glass by a micron. A 3 a.m. calibration check turns into a ritual. Power cycle the lamp, take a second exposure, overlay lines, look for the serpentine wiggle that ruins everything. Meanwhile, others point to Mg isotopes. If the relative abundance in a cloud is Earth-like, the line centers drift a bit. That can masquerade as alpha moving. The debate grows teeth. Either the universe has a preferred direction at the parts per million, 10^6 level, or a dozen small, harmless assumptions conspired to draw a dipole on our sky. Parallel to the telescope arguments, an older witness sat in rock, Oklo. 2 billion years ago in Gabon, a uranium deposit went critical. The isotopes it left behind depend sensitively on nuclear resonance energies, which in turn depend, through a messy chain, on alpha and on the strong force. When physicists back out what those resonance shifts would be if alpha had drifted, they find room for only tiny changes, parts in 10^7 or tighter over billions of years, in line with classic Fuji-style analyses. Not zero, but thin margins. Oklo fenced off the wildest possibilities and forced the sky claims to thread a narrow alley. Back on Earth, the lab clocks woke up. If alpha breathes, different atomic transitions should disagree in time. A strontium optical lattice clock ticks with electrons dancing between energy levels that scale one way with alpha. An aluminum ion quantum logic clock scales another. A microwave hydrogen maser tunes yet another knob. Compare them year after year, through seasons, solar cycles, and altitude changes, and you're not just keeping time, you're eavesdropping on the universe's control panel. Here's a micro-story from that front line. In a dim room, atoms cool to microkelvin, suspended in a web of laser light. A technician nudges a piezo by a billionth of a meter to kill a drift. The beat note between two clocks, the rhythmic whoop-whoop in a spectrum analyzer, shrinks to a thread. Weeks later, they fold the data, any sinusoid with a 1-year period, any drift linear with time, mostly silence. The limits tighten. If alpha is moving today, it's doing it below the 17 per year mark. Brutal. Not a death sentence for variation, but a cage with bars close together. While that was happening in the lab, the telescope world upgraded its ears. Laser frequency combs replaced calibration lamps. Vacuum-stable spectrographs sat on granite slabs, temperature controlled to the millikelvin. New surveys reported nulls or small shifts without a clear dipole. The fight became honest. Remove every known systematic and see what's left. Some datasets still prefer a dipole by a few sigma, others don't. Either way, the error bars got honest enough to matter. What nobody knew at the time, as the first dipole plots made the rounds, was just how much these arguments would feed cosmology and ignite careful reanalyses of isotropy itself. If alpha varies across the sky, isotropy, the core assumption that physics looks the same in every direction, takes a dent. If alpha drifts with cosmic time, the physics of recombination shifts, which slides the cosmic microwave background's acoustic peaks. That ripples into how we infer the Hubble constant and the age of the universe. It's not just chemistry, it's the scaffolding of cosmology. This was the moment everything changed in tone. The question stopped being, is alpha constant? And became, if it isn't, what's moving underneath? Because alpha isn't a single knob. It's a ratio involving the electron charge, Planck's constant, and see something deeper would have to be flexing. And if something deeper flexes, it can imprint a direction, a time dependence, or both. In the aftermath of 2 decades of sky and clockwork, we sit with an uneasy consistency. Alpha looks stubbornly steady in the lab today. The ancient rock allows only tiny drifts over eons. The sky still holds a hint that could be calibration or could be a cosmic breeze. Life's recipe seems robust here, maybe only here. To understand why alpha would move at all, we need a suspect that can turn knobs gently, everywhere, and yet hide from most tests. That suspect isn't a new particle we catch in a collider. It's a field that bathes space, slow rolling, changing the rules by whispers. If it's there, constants aren't constants. They're the local weather of a deeper climate. Ghosts in starlight, quasar spectra, and the dipole claim. While the lab tried to hear alpha breathe, the sky whispered in a different accent. Quasars, bright beacons at the edge of time, shine through filaments of intergalactic gas. Each cloud along the line of sight stamps a barcode of absorption lines onto that light. If alpha changed, the spacing of those bars would shift in a pattern you can't fake with a single element. It has to move across different species in a coordinated way. The many-multiplet method was the scalpel. Instead of trusting one doublet, researchers lined up transitions from magnesium, silicon, iron, chromium, nickel. Each transition carries a sensitivity coefficient, call it Q, that tells you how much that line's energy shifts if alpha nudges. Stack enough lines with different Qs, fit them together, and any consistent alpha change pops out of the noise like a watermark. Here's the stakes. If that change points in one direction over there and the opposite direction over here, then the universe has a preferred axis. Cosmology assumes isotropy, that on large scales, it looks the same in every direction. A dipole in alpha dents that assumption. It doesn't smash it, but it forces us to redraw the frame we measure inside. Action step by step. Keck's high-resolution HL spectrometer gathered hundreds of quasar spectra. The fits leaned towards smaller alpha in the distant past along its patch of sky. Then the very large telescope in Chile, with a different spectrograph and a different view, suggested the opposite in its hemisphere, alpha a hair larger. Combine them and the map didn't flatten. It twisted into a dipole. One pole prefers alpha down, the other alpha up, at roughly parts per million. Meanwhile, something else was happening behind the terminal screens. Calibration lamps, thorium-argon sources, etched reference lines used to map pixel to wavelength. But those lamps weren't perfect. Lines blended, orders curved. Temperature gradients across a meter-long spectrograph nudged optics by microns, warping the dispersion relation. One night at 3 a.m., a researcher relit the lamp, took a second exposure, and watched the line fit residual snake by a few meters per second. Tiny, yet enough to mimic a whisper in alpha if you were unlucky and trusting. Critics traced distortions, small, smooth wavelength stretches that varied across orders. Slit illumination changed when seeing conditions wobbled. Fiber feeds reduced but didn't erase it. Some groups re-reduced the same raw data with different pipelines and watched the dipole amplitude inflate or deflate. Others targeted specific systems with narrow metal lines less prone to blends, and the signal weakened. Parallel action in a different lab. Laser frequency combs arrived. These devices paint an evenly spaced ruler of absolute frequencies onto the detector, replacing messy lamps. Spectrographs like HARPS and espresso were stabilized in vacuum, pressure-locked, temperature held to the millikelvin. On these instruments, the calibration serpent had fewer places to hide. Early results leaned null or inconsistent with a strong dipole. Not a clean acquittal, just stricter cross-examination that put the boldest claims under pressure. Stakes for people showed up in small human ways. A grad student built a Monte Carlo to simulate quasar absorbers with non-terrestrial magnesium isotope ratios. Vary the isotopes, the line centers shift independently of alpha, smuggling in a false signal. Another team checked intra-order distortions by comparing telluric absorption lines imprinted by Earth's atmosphere with the lamp solution. The corrections helped, but didn't erase every anomaly. Across town, a different group reanalyzed only the highest signal-to-noise systems and found less evidence for any drift at all. So what did it change? Impact arrives in two layers. First, even contested hints forced the community to design instruments as if the dipole were real. Comb-calibrated, fiber-fed, vacuum-stable spectrographs became standard for precision cosmology. That engineering push pays dividends far beyond alpha. Exoplanet hunts, redshift drift tests, even measurements of cosmic acceleration with gravitational wave sirens cross-calibrated to optical spectra. Second, the combined datasets, Keck plus VLT, still prefer a dipole at a few sigma when analyzed in the original framework, even after known systematics are modeled. That preference isn't decisive. It's a standing invitation to try to break it. On the other hand, independent campaigns report nulls within tighter error bars. Either outcome tightens the noose. If variation exists, it must thread a needle between instruments, sky positions, and absorber chemistry. If it doesn't, we've just mapped the instrument ghosts with unprecedented fidelity, and that map now guides every new spectrograph design. Meanwhile, something else bubbled in theory. A spatial dipole is exactly the sort of imprint a light scalar field could leave if its value today varies slowly over horizon scales. If that field couples to electromagnetism, alpha becomes space's local weather. You'd expect mild gradients, not wild swings. You'd expect small temporal drifts, perhaps modulated by gravitational potentials, and you'd expect equivalence principle tests to feel a faint tug. That linked the quasar plots to laboratory searches and to lunar laser ranging in a single storyline. Human moment one more time. A researcher stares at residuals after subtracting every known distortion and whispers, "What's left?" Not triumph, not despair, just the feeling that either the sky is telling us a quiet secret or our instruments are almost but not quite silent. In the aftermath, the field moved with better tools, stricter priors, and a shared caution. Don't average away a signal, don't amplify a ghost. Even null results matter. They fence alpha's spatial wanderings to parts per million over gigaparsec scales, and its temporal drift to less than a part in 1017 per year today. While that was happening in Chile and Hawaii, a clue had been waiting in Gabon for 2 billion years, engraved in uranium and samarium. If the sky hints at a dipole, the Earth's crust holds a stopwatch, and that ancient clock has something blunt to say about how far alpha can roam. Reactor in the jungle, Oklo's ancient stopwatch. While telescopes argued with calibration lamps, a different kind of instrument was discovered in red laterite and jungle heat. In 1972, at the Oklo uranium mine in Gabon, a shipment's assay came back wrong. The uranium-235 fraction, normally 0.72% in nature, was short, not stolen, burned. The ore had less U-235 than any known terrestrial deposit should. Miners saw a bookkeeping problem. Physicists saw a fossil reactor. Here's why that mattered. 2 billion years ago, the natural U-235 abundance was higher. Radioactive decay hadn't yet whittled it down. Groundwater percolated through rich ore, moderated neutrons, and in pockets sustained a chain reaction. It wasn't mythology. It ran intermittently for hundreds of thousands of years as water boiled off. The reaction paused, water returned, and it resumed. Nature built a reactor with no blueprints, only geology and time. The stakes are sharp. A sustained chain reaction leaves fingerprints, isotopes out of balance, rare samarium and neodymium fractions that don't match ordinary geochemical processes. Those fractions depend on nuclear resonance energies, the precise positions where a nucleus is eager to capture a neutron. Shift those resonances a hair, and the reaction's byproducts change. Those resonance energies, in turn, trace back to the strengths of forces, primarily the strong force, but with threads to electromagnetism through the fine structure constant alpha. If constants drifted over eons, Oklo would show it in the ash. Action moved from shovels to mass spectrometers. Analysts pulled cores from the reactor zones, slicing time through minerals. They measured samarium-149, a notorious neutron poison, and its daughter samarium-150. They checked neodymium isotopes, xenon trapped in mineral bubbles, little time capsules of fission. The patterns weren't random. They matched what a reactor would cook, given cross-sections that depend sensitively on where a nuclear level sits relative to neutron energies in water-moderated conditions.